In this video, we are going to discuss acetal hydrolysis, which is essentially taking an acetal that we've generated and reforming the carbonyl from which that acetal was derived. Now, acetals will specifically be hydrolyzable, or I should say they should undergo hydrolysis under aqueous acid conditions. Therefore, we could say that acetals are unstable. They will react when treated with aqueous acid. But we would say that acetals are stable. They will not react with aqueous base. There is no reaction under aqueous base conditions. And those acetals, the carbon of the acetal, will not react with amines, cyanide ions, Grignards, hydride donors. That is to say, if I have a carbonyl is an electrophilic group, and if I had a Grignard reagent floating around, that would attack the carbonyl carbon and break the pi bond. But if I have a Grignard floating around an acetal, it does not recognize that acetal as an electrophilic carbon. That acetal will not be reacted by amines, cyanide ions, Grignards, or hydride donors. It will also not react and transform under aqueous base, but it will react under aqueous acid conditions. And what we're going to say is that the carbonyl that we generate as a result of the hydrolysis, the H2O nucleophile that's adding in, that becomes the carbonyl oxygen. And then visually, notice that we're severing the bond from the former carbonyl carbon to each of those oxygen atoms, and those separately then become alcohols as we hydrolyze. Okay, those are the hydrolytic breakpoints as we do acetal hydrolysis. Now, in a later video, we'll talk about protecting groups, but acetals can be utilized as protecting groups because when you take an aldehyde or ketone and turn it into an acetal, what was an electrophilic carbonyl carbon is no longer an electrophilic carbon. But I'll do a whole video series, separate videos for protecting group usages, right? So we're going to imagine taking our acetal, cyclic acetal, and reacting with H2O and H2SO4, aqueous acid. Now, let's also stipulate that here there's no heat required. This could be done with or without heat, but the heat is not required. Now, we ultimately want to disconnect that carbon from each of those oxygen atoms, and to disconnect one of those oxygens, we would first have to protonate it to make it into a better leaving group. Now, you can start by protonating either of those two oxygen atoms, but we need to protonate that oxygen, which makes that now into a better leaving group. And then to break off that oxygen, what we need to do is collapse a lone pair from the other OR portion, collapsing the lone pair from the one that's neutral. That will form a pi bond and break that carbon to oxygen bond. Now, because this was a cyclic acetal, that alcohol leaving group is still hanging out within the chain. Now, at this point, we have a charged carbonyl, and that's water's window of opportunity to attack and bond into the structure. After it's connected into the structure, that oxygen has a charge positive to it. So what we need to do is deprotonate the oxygen atom. That will stabilize its linkage, and that brings us then to the hemi-acetal intermediate, where we have an OH group and an OR group bonded to the same carbon. Now, we'll keep in mind that because we're doing acetal hydrolysis, we're at result going to kick out that portion there as another leaving group. But before I kick it out, I need to protonate it to make it into a potential neutral alcohol leaving group. Okay, I protonate the OR component, just like we did to begin with, right? I protonate that to increase its leaving group propensity. Once it's protonated, that could then leave as a 1,2-diol neutral alcohol leaving group. And to kick it out, I would have to fold down a lone pair from my neutral OH component to form a pi bond. And that would then expel a neutral 1,2-diol alcohol leaving group. From there, we have one more step, and that's deprotonating the carbonyl oxygen to form a carbonyl compound. So let's recap that mechanism. We need to protonate in the first step. We protonate to increase the leaving group propensity of that oxygen atom. We then collapse our lone pair from the neutral OR component, breaking off that component as an alcohol leaving group. This is water's window of opportunity to attack and bond into the structure. After water has added in, we need to deprotonate the oxygen atom, making that neutral, decreasing its leaving group propensity and stabilizing its linkage in the structure. That's now our hemiacetal intermediate. So what we need to do with the hemiacetal intermediate is protonate the OR component. And I need to protonate that so it then could leave as a neutral alcohol leaving group. And it would leave when the OH component folds down its lone pair forming a pi bond. That forms a protonated carbonyl, and finally, we're going to deprotonate to form the neutral carbonyl. And you'll notice that carbonyl carbon is forming at the carbon where the two oxygens were formerly bonded. Such that if you ever have an acetal and you're reacting, with water and acid, how you visualize that transformation is this. You imagine drawing a carbonyl at the carbon where each of those oxygens were bonded. So we say reform C double bond O. We reform a C double bond O at the carbon that those two oxygens of the acetal were sharing. What you're then going to do is imagine breaking each of those carbon to oxygen bonds in your acetal, and those will then separately become alcohols, and they will leave at different time points in the mechanism. So we'll regenerate a carbonyl, and the carbonyl oxygen is coming from our water, which is adding into the structure, and we kick off our 1,2-diol component. Now, let's show a few more examples of this. If I took this structure here, which is an acetal, and I react with water and acid, I'm going to imagine reforming a carbonyl at that carbon where each of those OR oxygens are bonded. So I'm going to reform a carbonyl at that position where I put the asterisk. Then what I need to do is imagine breaking each of these carbon to oxygen bonds there. That would then form a 1,2-diol. Okay, that's the shortcut. Instead of having to think all the way through the mechanism at the carbon that the two oxygens are sharing, we reform a C double bond O. Then you disconnect each of those oxygens from the carbon that they're sharing from our acetyl carbon. And then you imagine bonding a hydrogen to each of those, forming an alcohol out of both oxygens. So this was a cyclic acetal, and because that was a cyclic acetal and the oxygens were sharing the carbon, we ended up forming our 1,2-diol. Let's imagine that you have a regular old acetal, it's not cyclic, and we react with water and acid. I'm going to imagine reforming a C double bond O at the carbon that they share. That is to say, I'm going to form a C double bond O here. Then I'm going to disconnect each of those oxygens from the carbon that they're sharing, and that would then be creating two separate molecules of ethanol. That's one ethanol, that's the other ethanol. But notice I'm using the exact same strategy in each case. Moving on to another example, this structure was given on a former exam at UNC, and a lot of students got it wrong. This one is subtle because notice how here we have the acetyl carbon. That's our acetyl carbon because we have two OR groups bonded to that carbon. And we're reacting with water and acid, so we know we're doing our acetal hydrolysis. And that carbon is just connected to two hydrogens. What I need to do at the carbon that each of those oxygens are sharing is reform a C double bond O. That means that here the carbonyl that we reform is that of formaldehyde, the simplest aldehyde. And I think that's what makes this kind of tricky, because it's hard to see that carbon as a former carbonyl carbon, but it would be. And then we need to break each of those connection points that the oxygens have to their carbon. I'll maybe do that in blue here, just to visually distinguish. We're going to break those off and then imagine those becoming alcohols. And it looks like those components are identical. We've got a benzene ring, a carbon, and then an OH, and we would have two of those generated as a result of this acetal hydrolysis. Okay, to recap the strategy, you will look at your structure of your acetal, and at the carbon that each of the oxygens are bonded to, which is your acetyl carbon, you want to imagine reforming a carbonyl. Reform a C double bond O. Then what you need to do is you need to break each of those carbon to oxygen bonds, and then separately imagine each of those becoming alcohols. And in this case, those alcohols are connected through the same chain. We did that same strategy here, forming our ketone, and then two separate molecules of ethanol. And with this one here, former exam question, we had to recognize that we were reacting in acetal because there's two OR groups bonded to the same carbon. Looking at that acetyl carbon, we'll imagine reforming our C double bond O at that carbon. And then we need to disconnect each of those oxygens from the carbon. And those will then separately become their own alcohol, which happen to be identical in structure. All right. Now, you'll often see the cyclic acetal referred to as a protecting group, but I want to clarify that really any acetal is technically a protected former carbonyl, meaning if I were to react this right here with ethanol and H2SO4 catalytic, that would generate an acetal, and I've effectively protected this carbon by generating the acetal. So you can protect an aldehyde or ketone by really forming any acetal. It's just that usually if we are trying to protect an aldehyde or ketone, we will generate our cyclic acetal by reacting with our 1,2 diol and catalytic acid. That's the most common way that we will protect, but really any acetal can cause protection of an aldehyde or ketone. All right. Now, you definitely need to know the mechanism of deprotection, and I think the strategy of visualizing the deprotection is even more important because you can legitimately see exam questions in a predicting product scenario where you have to draw the former carbonyl, or the carbonyl that would be reformed, and then the alcohols that were part of going into forming the acetal.